Good morning, students. Is my voice audible?
Yes, sir.
Okay, let me share my screen from my end. Just check and let me know if the screen is visible. Are you able to see my screen?
Yes, sir.
Okay. So very good morning, students. In the last week, we were discussing about single linked list and its operations. And in the last lecture, if you remember, we have seen various operations of single linked list in terms of create, delete, and traverse. In create, we have seen three options like create at start, create at end, and create at given location. And same is the case with the delete operations. We have seen delete at start, delete at end, and delete at given location. And we have seen traverse operation also. So in this singly linked list, if you remember, this singly linked list is basically a list which is comprising of collection of nodes where each node has two parts. One is the data element and another is pointer to next node. So in order to create this node in our C programming language, we use the concept of structure. So we write structure like struct node, node and struct node, and we build int data and struct node pointer to next. And for create operations, we need to allocate the memory in C. So for that, we are using the syntax of malloc, if you remember. And for releasing the memory, wherever we perform delete operation, we are releasing the memory for those particular nodes. So we are using free function in that case, right? Now, uh, uh, in all these operations, if you remember, we were having one external reference pointer, which we call it as start. So what was start? Start was a external reference pointer which we used in order to. Are you able to hear my voice, students?
Yes, sir.
Yes, sir.
Yeah. There was some network glitch from my end. Okay, so start was one external reference pointer which was useful for pointing to the first node of our linked list, right? Now, today we are going to continue with one of the other variants of single linked list, in which we will be having not one but two external reference pointers. Okay, so up till now, whatever linked list I had taught you, if you remember, suppose say for example my linked list is having three nodes. So suppose this is my first node, its next is pointing to the second node, and its next is pointing to third node. Now this is my last node, so its next is pointing to null, and the external reference pointer which I say is in the form of start, which points to the first node or starting node of our linked list, right? So this is a normal single linked list which we have studied up till now. So it will have some data. Suppose I take that data in the form of say 10, 15, 20. Okay, so this is the data in my single linked list. Now it is not compulsory always that you will have only one external reference pointer. You may have many external reference pointer. For that matter, whatever operations we discussed in the first linked list, there also we used something called as P and Q. What were this P and Q? This P and Q were also pointers, right? These were temporary pointers rather, which were pointing to some node which we were trying to create, or which we were trying to delete, or which we were trying to find in our linked list, right? So we were using these pointers as temporary pointers for performing those operations. Okay, so these were also external reference pointer, but we can say that these were not permanent pointers like start. Like start is always a permanent pointer which we try to maintain for the starting node of our linked list. But still, like start, this P and Q were also external reference pointers for us, right? Now, similarly, we can have many such external reference pointers in our linked list. And not only that, we can also have permanent reference pointers like start. One such permanent reference pointers which I can have is the last reference pointer. Is the last reference pointer. Now, what is this last reference pointer? This last reference pointer will help me to point to the last node of my linked list. This will help me to point to the last node of my linked list. So what is last external reference pointer? Last external reference pointer is a pointer which will help me to point to the last node of my linked list. It will help me to point to the last node of my linked list, right? Now, every time you perform an operation, it is our responsibility that if the last node of our linked list is getting changed, then we need to update this pointer. Like when we did the other 6 operations in the first type of linked list, every time a start was getting changed, we were updating the value of start. No matter we are doing create at start or create at end or create at given location or delete at start, delete at end or delete at given location, in any of these operations, if the value of the first node or the starting node is getting changed, then we were updating the value of start pointer. Now if I try to represent my linked list with 2 external reference pointers called as start and last, where start will now point to the first node of my linked list, whereas the last will point to the ending node or the last node of my linked list, then in all the 6 operations that we perform, we have to maintain start also and we have to maintain last also. So by performing of any operation, if my last node is getting changed, then it is our responsibility that we should write a logic in order to maintain that last reference pointer. In order to maintain that last reference pointer. Now, if you remember, when we had only one external reference pointer in the form of star, and when our linked list was empty, at that time we used to represent that linked list like this, that our start is pointing to null, that our start is pointing to null. Now when we have 2 external reference pointers in the form of start and last, and if our linked list is empty, then we should maintain both the pointers. We should maintain start also and we should maintain last also. So when our linked list is empty, that time start is also null and last is also null. So when our linked list is empty, I again repeat, when our linked list is empty, initially when we have only one external reference pointer start, that time start was equal to null, right? Which was indicating us that linked list is empty. But now when we are representing our linked list with 2 external reference pointers, that is start and last, then in that case, if our linked list is empty, start will be also pointing to null and last will also be pointing to null. In the case for linked list is empty. Now, when we go for operations like all the creates and all the deletes as I suggested, then every time any operation is carried out, and due to that operation, if our values of start and last are getting changed, then it is our responsibility to update those values. So we need to discuss those operations one by one again, right? And we should also identify that what could be the probable change that will be happening in this single linked list program. Now the logic of operations remains same. Okay, so the concept remains same. The only change is that every time we need to think of this one external reference pointer now, that is last. Whether our last node is getting changed due to that operation, and if it is getting changed, then we need to update its values. Then we need to update its values. Did you understand this? Now, if we are trying to implement this type of linked list, so consider that this is a blank program now of a single linked list, okay, which I have written already here in front of you, where now I am having all the 8 choices in the form of create at start, create at end, create at given location, delete at start, delete at end, delete at given location, traverse and exit. I am taking the choices and this will run in the do while loop. If you see here, I've already declared a struct node like we have done in the earlier single linked list program, and I have declared only one external reference pointer as of now, which is start. You can see here, that is node pointer start is equal to null, and P and Q are the ones which we are using as temporary external reference pointers for the creation, deletion or finding purpose. Now apart from this, as I told you, there will be one more external reference pointer in our program which will be called as last, and initial value for this last will be null, like our initially when our linked list is empty, start was null. Similarly, initially when our linked list is empty, now last will also be null. Now what is the use of having these 2 external reference pointers? See, when our linked list will grow long, then it is always easy for us to reach to a last node if we have one external reference pointer last. Otherwise, we have to keep on traversing the linked list from first node till the last node. If you remember operations like create at end, when we were discussing, for reaching to that end, we have to traverse that queue from first node till the last node, right? And if we have external reference pointer maintained for last, then it will be very easy for us to create at end. You're getting this, right? So to improve the efficiency of the algorithms which we are going to further solve using this linked list, we may have multiple external reference pointers also, and one such additional reference pointer which we are discussing today is in the form of last. Okay, where this last is helpful for us to store the information about the last node or the ending node of our linked list. Now this is how we have created. Now we'll have the first operation. Okay, now let us have the first operation on the basis of this, that is create at start. Let us have first operation, that is create at start. I will be explaining few operations to you in today's lecture, and other operations which I'll be telling you today at the end of this lecture should be tried by you at home as a part of homework. Okay, because already I have taught you the other operations in normal linked list, right? Let us discuss few operations here today. Suppose we are doing create at start. Suppose we are doing create at start. So with create at start, okay, with create at start, now how the diagram will look like? Start is pointing to null and last is also pointing to null when our linked list is empty. This is our first case, right? What is our first case? Linked list is empty. Our first case is linked list is empty. Linked list is empty. P is the node which we are trying to create. This is our P. The data is 10. So after we create, how the output should look like? So output should look like this, that now starting node is nothing but the P node, correct? Whose data is 10. P's next should point to null, and now this is one thing extra that is going to happen, that now this last should point to P. This last should now point to P. Are you getting this? This is extra thing that is happening. So let us go and write logic for this. Second case will be linked list is containing some elements. Let us complete that also and then we'll go and write the logic. Second case is linked list is containing some elements. So when linked list is containing some elements, in that case, let us take a linked list, right? So suppose this is my first node, that is start. And this is my last node. So this is external reference pointer called as last, which is pointing to the last node. The data are in the form of 10 and 20. The data is in the form of 10 and 20. Now we are doing create at start. So the node which we are trying to create is P. Node we are trying to create is P. So the logic is very straightforward. We have seen this already, right? P's next is start. P's next is start, and start is P. P's next is start. This will be the first statement. Second statement is start is P. Sequence important because if we don't follow the sequence, cycle will be created over here. Okay, P's next is start and start is P. Now whether last is getting changed due to this? Last is not getting changed. So there will be no change in this part of the logic. There will be no change in this part of the logic because the value of last we are not changing due to create at start when our linked list is containing some elements. When our linked list is containing some elements. Are you getting this? So let us quickly go and write logic for this. Okay. So in this switch, we are writing our first case, which is create at start function. And we will also write traverse function to check whether our create has been done properly or not. So I'm declaring two functions now at the top, that is create at start and traverse, and let us go and write the logic for that one now. Create at start. So first we will do a malloc is equal to node pointer malloc size of node. We'll ask user to enter the data. This is common. We have done this in a normal linked list also, right? So enter data element. We will scan this data in piece data. Now, if our linked list is empty, start is pointing to null, we'll have one case, else our linked list is containing some elements, right? So this is condition when linked list is empty, and this is condition when linked list is containing some elements. When our linked list is empty, that time what we have seen, piece next is null, correct? What links I have shown you, piece next is null, this first one, piece next is null, then start is p, and last is p, start is p and last is p. So we'll write those statements, start is p and last is p. And what was the else part? Else part was very same like our normal linked list with one external reference pointer. That is, piece next is start and start is p. Piece next is start and start is p. So this completes our create at start. This completes our create at start with two external reference pointers, that is start and last. Now let us write logic for traverse also quickly, that we can check whether create at start is running properly or not. So in this also we write one condition, that if our linked list is empty, we print to our user that linked list is empty. So this condition is to check linked list is empty. Else if the linked list is not empty, we print the values. So for printing, we take q initially as start. The loop was, if you remember, while q is not equal to null. This is the same traverse which we have done in single linked list. I am doing the same traverse here to print all the elements. We'll start from the first node, keep on jumping till we reach to the end of our linked list, where our q will become null in that case, and we'll print all the data elements, right? So printf, print elements one by one on next line. Okay, and this data will be nothing but q's data. We print, then we perform jump by q is equal to q's next. In this and print all the elements of our linked list. We'll print all the elements of our linked list. We'll quickly try to save this, compile this code. I have forgot to include stdlib. There is some spelling mistake of traverse. So this got compiled and now I'm executing it. So create at start we have done, right? So I'm doing create at start with option 1 first. Now the linked list is empty. The element that I try to create is here is 10. Okay, so then I do a traverse. So you can see here element 10 is created properly. Again I do a create at start, and I enter data element as 20. I enter the data element as 20. Again, if I traverse now, you can see here 20 and 10. You can see here 20 and 10. So we are getting the desired output. We are getting the desired output here in this case. So this was our first function of create at start. This was our first function of create at start. Similarly, now let us do the second function, that is create at end. Let us do now the second function, that is create at end. Okay. Now again, when we are doing create at end, let me copy this page. Okay. Now when we are doing create at end, the next operation, our second operation, that is create at end. Again, we have two cases. Linked list is empty or linked list is containing some element. Linked list is empty or linked list is containing some elements. Now when our linked list is empty, start and last both will be pointing to null. P is the node which we are trying to create. P will be the only node in our linked list. So P's next will be null. Start will be pointing to P. Last will be pointing to P. So this will be same as that of create at start. Right? There will be no change when our linked list is empty, because the new node which we are trying to create will be the only node in our linked list, which is P. So P's next will be null, start will be P, and last will be P. Change will come when our linked list is containing some elements. Change will come when our linked list is containing some elements. So let us take an example for that. Let us take an example for that. So I am constructing a linked list which is containing some elements. Suppose this is that linked list. Let me take two nodes so that it will save space. So this is the last external reference pointer which is pointing to the last node of our linked list, which is currently pointing to this node. This is 10 and this is 20. So this is my current linked list. P is the node which I am trying to create now. This is that P node which I am trying to create. This is the P node which I am trying to create, correct? Suppose the data of this node is 30, suppose. Okay. Now what are the things we need to do? If this node has to become, this P has to become last node, then its next should point to null. Its next should point to null, right? And this node's next, this node, current last node, which is 20, its next should point to this P. Now if you remember, when we implemented singly linked list with one external reference pointer start, in order to find this node, we were giving a label called as Q, right? And we were jumping that initially Q is equal to start, then while Q's next is not equal to null, we had written a jump of Q is equal to Q's next, and we had reached to the last node of our linked list, which is this node, for finding the last node. Now here we don't need that logic. Why? Because already we have maintained this last pointer, which is pointing to the last node. This is pointing basically to this node. This last is not a node. Again I repeat, this last is just an external reference pointer which is pointing to the last node. Which is the last node? 20. Which is the last node? 20. So this pointer last is pointing to this node, that is 20. So we want to make 20 is next as 30. So simply we can write last next is P. What is this node? This node is nothing but this is last only, right? So what we have to do? We have to do this. That is last next is P. Correct? P's next is null. After I do this, now I should change the value of last. Now earlier this last was pointing to this node 20. Now this last should point to this node, that is 30. Are you getting this? Because now this P wala node is the last node of our linked list. So what we need to do? We need to make last next as P. This we have to do first. because earlier we have to utilize the value of existing last and then change the value of last. If you change the value of last before, then you will not be able to get value of previous lasts, right? So first I will write statement lasts next is equal to p. So this 20's nodes next will become 30 now with this one. Then p's next is null. This we can write anytime because this is not causing us any problem in the sequence. This we can write first also, or this you can write at the end also. That is p's next is null. That is p's next is null. So this statement will be executed, that is p's next is null. Then we have to update the last value. Then we have to update the last value, right? So this last should now be pointing to p. This last should now be pointing to p, which is the newly created last node for us. Which is the newly created last node for us. Are you getting this, my dear students? So let us go and write logic here in the program for the second function, that is void create at end. That is void create at end. So for that we will add another case, that is case 2 create at end. And let us write the body now. Void create at end. Again here we need to do a malloc first. Allocate the memory. Then we need to ask our user to enter the data. We need to scan that data. This data. After we scan that data, we need to check whether our linked list is empty or it is containing some element. This is linked list is empty and this is linked list containing some element. Linked list is empty. Linked list is containing some element. When our linked list is empty, the logic of create at end is same like create at start. So what three statements will write? P is next is equal to null. P is next is equal to null. Start is equal to P and last is equal to P. P is next is equal to null. Start is equal to P and last is equal to P. Now in the else part, we have to make existing last nodes next as P. Existing last nodes next as P. Then this P, which is our new last node, its next has to be made as null. And we have to define the value of last as P, because due to this now last is getting changed. Because we are doing create at end, right? So ending node is getting changed. So the newly created node is now the last node. So that's why we are changing value of last. That is last is equal to the newly created node P. Let us quickly try to save this. Compile and run this. Oh. So let me do create at end, second option. Then now linked list is empty. So I have entered the data element as 10. I have entered the data element as 10. Roll number 24. Roll number 24. Are you there?
Yes, sir.
Yeah. Now I am pressing create at end again. Okay. And I am entering 20. What will happen as far as the logic is concerned?
If we traverse, then the output will be 10 and 20, 10 20.
10 20. So we are doing create at end, right? So currently
Yes.
what is the situation, whether linked list is empty or linked list is containing some elements?
Linked list is containing some element.
Linked list is containing some elements, right? Now who is last as of now before entering this data?
The last node is 10.
10, correct. Start is also 10, last is also 10.
10.
So the moment I press this enter, what will happen? 10's next will be
Will
20.
be yes.
20's next will be
Will be null or last.
no last. 20's next is null.
Yes, yes, null.
20's next is null. See, again, in diagram, don't visualize last as an other separate node. Last is just a pointer. Okay. So 20's next is null.
Null.
20's next, and then what is last?
Last is 20.
Correct. Last is 20. The third statement, what we have written, what is meaning of that statement? Now this newly created node 20 should become the new last node of our linked list, right? So last is 20. Last is 20. So we have, once I press this enter, these three statements got executed. Now if I traverse, oh, there is some mistake. It seems I have printed something else. While scanning, I have not used ampersand. That's why the address is got. Quickly save and compile and execute once again for you. So I'm doing a create at with data is 10. Again I'm doing create at end with data as 20, and now I am doing a traverse. So you can see 10 and 20 are getting printed. 10 and 20 are getting printed. How this function? First it assumed that first the linked list was empty, so 10 was the only node. So start was also 10 and last was also 10. The moment we did create at end again, then 10's next got assigned to 20, 20's next got assigned to null, and last got assigned to 20. Last got assigned to 20. Is it clear, my dear students? I'm doing an exit from here. Now I'll demonstrate one delete for you. Okay, I'll demonstrate one delete operation. Before we see at given location, I'll demonstrate one delete operation for you. Okay, so let us see delete at start. Let us see delete at start. Delete at start. Now in delete at start, if you remember, we had two cases. That was linked list is empty and linked list is containing some elements. Now when linked list is empty, then in that case, in that situation, we just print to our user that there is nothing to delete, right? So delete cannot be performed. So that will be same here also if we have two external reference pointers, right? So if start is equal to null, delete cannot be performed. Second situation is linked list is containing some elements. So let us take an example for delete at start with linked list is containing some elements. So suppose I am taking say two elements in my linked list. So these are my two nodes. This is my first node and this is my second node. This is start and this is last. The data are 10 and 20, suppose. Now I am doing delete at start. Now I am doing delete at start. Now I am doing delete at start. So which node has to be deleted? This node. Node 10, correct? Node 10 has to be deleted. So this becomes P for me. How we do that? P is equal to start. How we do that? P is equal to start, correct? Then I have to delete this. For this I'll write free P. For deleting this, what I'm going to write? I'm going to write free P. But before I write free P, I should also adjust my links. What is the adjustment that I need to do? Start is equal to starts next. Start is equal to starts next. Start is equal to starts next. So now this start will be pointing to this node. This start will be pointing to this node. Are you getting this? And then I can write free P. So P is equal to start is this node. Start is equal to starts next means start will point to this node, that is 20, and free p will release this memory. Are you getting this? Now suppose there is only one node in my linked list. Let us test what will happen. This is my start, which is pointing to 20. This is null. This is last, which is pointing to 20. So after I delete this, this is the output, right? Correct. Now again I am pressing delete at start. Now again I am pressing delete at start. Rohit Gavas आहे का? Rohit Gavas. Rohit Gavas. Are you there in this lecture? Sanket Suryavanshi.
Yes, sir.
Who is here? Your name?
Sanket Suryavanshi.
Rohit.
Yeah.
Rohit also.
Rohit. Okay, Rohit. Now you tell me, Rohit, that
Yes,
in this situation, see, this is the output of first delete which I have shown. Okay.
sir.
Now again I am pressing delete at start. So linked list is not empty. Linked list is containing some element. So it will go in this code. Correct? Tell me what will happen to this now.
Sir, then start will go to start will equals to null.
Correct. So first this will be P, right?
Yes, sir.
One statement at a time. So first statement is P is equal to start. So this will become P. Then next what? Start is equal to?
Null. No, sir.
Correct.
Start.
Correct. Null. Start is equal to starts next. So what is starts next? It is
Null.
null. So start will become null because once I delete this node, once I delete this particular node, linked list should become empty, right? So start should become null, which is happening by default, right? So that is correct. So start is becoming null. Start is becoming null automatically. Then free p. Correct. Free p will release this. But what about last? What should be the value of last when our linked list is empty?
Null.
Null. What should the value of last when our linked list is empty? It should
Null.
be null. Sanket Suryavanshi, are you here?
Yes, sir.
Sanket, did you understand the issue which I am explaining here?
Yes, sir.
See, if I execute only these three statements, this works well if we have two or more nodes. Okay. But when I have only one node remaining in my linked list, automatically my last is not going to get updated by these three statements. Correct? So I need to execute one more statement in that case. What is that statement? That last should be equal to null. So either I need to write some logic for executing one more statement over there, or I have to write one more case like linked list is empty, linked list is containing one element, and linked list is containing two or more elements. Are you getting this? What I am trying to explain?
Yes, sir.
Okay. So we need to have three cases now in this case, because only these three statements works well when we have two or more nodes. In that case, last is not getting changed by delete at start. But when we have only one node in our linked list, that time last is also getting changed because last should also become null. But with these three statements, only start is getting null, but last is not getting null in that case. So we should handle it separately. Are you getting this? So let us do that with help of code now. Let us do that with help of the code now. Let us write the function for delete at start, which is our fourth case. That is delete at start, and Let's write the function body for delete at start. As I told you, there are now first case is start is null. So when linked list is empty, what should be the output? Output will be delete cannot be performed. It cannot be performed. Now we have three cases. Linked list is empty. Linked list is containing one element. So when linked list is containing one element, that time starts next is null. We have seen this type of logic in delete at end of normal linked list with one external reference pointer. When we have three cases, how we write it? So when linked list is empty, this is the case that linked list is empty. This is the case when linked list is containing one element. This is the case when linked list is containing one element, and this is the case when linked list is containing two or more elements. It is containing two or more elements. So if starts next is equal to null, then P is the only node in our linked list. So P is equal to start, you can write, okay. Then we have to release this, we have to free this, but before that we'll adjust start and last. So start will be starts next, or directly we can write start is equal to null now, because when starts next is equal to null, the only node that we have in our linked list is P. Once we delete that P, start will also become null and last will also become null. Start will also become null and last will also become null. And then we have to memory of P. Before we free the memory of P, we printf that deleted element data is percentage D. What we have deleted? We have deleted P's data. We have deleted P's data. Correct? P is the only node, so P is equal to start. Once we delete the last node, start will become null, last will become null, and we print what the data of that element which we have deleted, and we release the memory of P by writing free P. Now, when our linked list is containing two or more elements, this logic will work well in that case, whatever we have written. That is P is equal to start is equal to starts next, and free P. In that case, we don't need to bother about last. In that case, we don't need to bother about last, right? So let us write those statements. P is equal to start is equal to starts next. We print the data of the node being deleted. So deleted element data is percentage D. That data is P's data. Data is P's data. Correct? And then we write free P. Then we write free P. In this case, we don't need to bother about last because we have two or more elements. So let us quickly try to save, compile, and execute this code. I'll create a linked list before. I have created a linked list with two nodes, that is 10 and 20. There are two nodes. Now I'm doing delete at start. Arti Kore, are you here? Arti Kore.
Yes, sir.
What will be the output?
Sir, if we do at delete at start, then only 20 wala node will be there.
Okay, so the output is deleted node is 10. Output is deleted element
Deleted.
data is 10. Because now we are deleting it at start, and in which case we have gone? In the third, is if मध्ये पण गेलो नाही, else if मध्ये पण गेलो नाही, we have gone in the else part, right? So we have gone in the else part where linked list is containing two or more elements. So 10 got deleted, right? Now, Arti, again I press delete at start. What will happen?
Sir, 20 will get deleted.
deleted element data is 20 will be printed, right? Now here
Yes.
we have gone in the second case, that is else if. Else if, that is starts next is null. So in this case, start will be also made as null and last will also be made as null. So deleted element data is 20. Correct? Now if I
Yes.
again do delete at start, what will happen?
So linked list is empty.
Empty. So it will print that delete cannot be performed. See, it is printing that delete cannot be performed. Dear students, what we have seen today is that we have represented singly linked list with two external reference pointers instead of one, that is start and last. Okay, that is start and last, and I have demonstrated three operations for you. Which three operations I have shown you? Create at start, create at end, and delete at start. Now there is a jackpot homework. You are excited now for this homework. You have to try create at given location. Okay, you have to try create at given location, then delete at end and delete at given location for this type of linked list. Okay, and one more good news, and any student will get an opportunity randomly to present this in upcoming lectures. CR ahega? Who is the CR?
Yes, sir.
CR, is my homework understood?
Yes, sir.
So I have taught you three operations, okay? And you know what is meaning of at location now, okay? You know what is meaning of end. You know meaning of creates and deletes. Only thing you need to do is you have to maintain last. Right? So these three cases you people have to try on your own as homework, and you all know there is a practical time slot also created, additional, and our practical will be on Wednesday if I'm not wrong. Yeah, one timetable is been posted by Mulla ma'am, right? So that in that slot, I will be asking students to present and I will be calling any random number. And those who will be remaining absent will lose marks for labs. Okay. So don't be under impression कि हम lecture miss कर देंगे, so answer नहीं देना पड़ेगा. So directly that experiment marks will become 0. If I call a particular student and if he is not present for that lab, his marks will become 0 for that lab. Okay, be present. Even if you make mistakes, for me it is okay. I'll correct you. But you people have to make an attempt. So today try to complete notes for the three operations which I have already taught. Plus additional what you need to do is you need to try these three operations also, which we will be discussing during the lab sessions. Is it clear? Any doubts in this? CR, any doubts in this?
No, sir.
So let me stop the screen sharing and let me take down the attendance.